Welcome to Hot Chips 31. Session 8, Packaging and Security.
I'm John Sell, and I'm introducing our next section, and it is going to cover some interesting packaging technology and some interesting security presentation. First, it's my pleasure to introduce Sanjeev Khushu, who's going to describe the Intel Lakefield hybrid CPU cores in a 3D package. Sanjeev is Vice President of Infrastructure and Platform Solutions at Intel. And he leads the Converged Mobility Initiative. And before Intel, he's spent a number of years at Qualcomm. He's going to be assisted during the question and answer section by Wilfred Gomes, who's a senior principal engineer at Intel and specializing in 3D stacking technology. And he spent more than 20 years working on mobile and client x86 processors. Sanjeev?
Get a pointer. Good afternoon. I'm Sanjeev. I'm excited to be here, and I'm super excited to talk about Lakefield. So what is Lakefield? So a few years back, we had a requirement within Intel to enable a new set of devices, what we call as converged mobility. It's a device in between a traditional laptop and a smartphone. So basically, it has a compute similar to a PC, but a form factor, mobility form factor, right? So what it meant is that we had to enable a best-in-class compute in a form factor which was much smaller than what traditional PCs had enabled. So the device is super thin. It needed to be super thin. It had to be lightweight, a fanless design. And also the standby power had to be much, much lesser than what would traditionally the PCs have enabled, not in like 20s or 30s of milliwatts. It had to be like in 2 milliwatts or 3 milliwatt range. So that was a requirement. So what it meant for SoC is that we had to actually obviously go to the latest process node. In our case, it was Intel 10 nanometer. And also we had to do significant improvements gen over gen from a previous generation 14 nanometer, right? So our standby power had to go down 1/10 compared to the previous generation. Our graphics was key for the converged mobility segment. Our graphics performance had to go up by 50%. And also the SoC core area, the SoC footprint, and the area around the SoC that includes the power management, it includes the memory, that area itself had to go down by 50%. And the overall Z of the product, the end product Z had to go down by 40%. So as you can see, there were like significant improvements that we had to do over gen. Like Lisa talked yesterday, in the compute industry, you have a trend line you generally follow, and you kind of stay within 10% of the trend line. But the kind of gains that we had to do gen over gen for Lakefield were substantial, right? I mean, you had to increase your performance by 50%, but at the same time, your standby had to go down to 1/10, right? The footprint of the whole SoC core area had to go down by 50%. So how do you do that? So how do you achieve that kind of performance gains in a single node jump, in a single generation, right? So that led to the birth of Lakefield. So I actually have this silicon with me. So you can see this is the real Lakefield silicon. I just got it shipped from Chandler this week. It's 12 by 12 cross 1, as you can see in the file. It's 12 cross 12 cross 1. It has 3 dies. It has the compute die, and on top of that is a base die, and then there's a memory pop on top of that, 4 gigabit memory. You've probably never seen anything like this before in the compute industry, a 12 cross 12 cross 1. So I mean, you see this kind of SoCs typically in a smartphone. Even in smartphone, 12 cross 12 is considered to be small. So that's what we're able to achieve with all the innovation that has gone into Lakefield. And this is our reference design. You may have seen this. This was presented by GB at the CES. So it's a full compute platform on a full PCB. It's a single-sided PCB. It is 30 by 123, single-sided, about 0.6 millimeter thick, and like I said, 30 by 123. So you have the entire compute on a PCB like this. This is the smallest ever that we within Intel have built. So now on this slide, I have a comparison of what Lakefield has enabled. At the top is a Lakefield dual display. Like I said at the beginning, our main intent at the beginning of the project was to enable like a new set of devices, primarily dual display devices. So that the first board that I just showed is a Lakefield dual display device. Without the modem, it is 30 by 123. If you include a 1 gigabits per second LTE modem, the dimensions is 165. Right? The one below that is a traditional clamshell design, like a single display design. So that itself, that the board is 30 cross 171. If you include LTE 1 gigabits per second modem, it's 213. So as you can see, this is the smallest board that we have been able to achieve, primarily because of how Lakefield Silicon was done. It was done in a way where you have a 3D die stacking, where you put the compute and base IPs in a single package. Instead of spreading them in X and Y dimensions, you go up in Z dimension. So in the board right below that is our latest optimized motherboard with the Gen-1 platform. So as you can see, that board is 30 by 252, I guess, and with 274 if you include the modem. And the one right below that is a competition board, which is in a similar capabilities as Lakefield. So as you can see that I'm going to talk about a little core area in the next slide, but the main intent of the slide is to show that the kind of improvisation that Lakefield has brought to the table in terms of the overall board area has significantly been improved compared to the previous generation. And the primary factor for that is the SoC. In addition to that, we have done optimizations like we built in EC-Lite architecture. We have done boot from UFS directly instead of using SPI boot. So as a result of that, the board area is pretty compelling. All right, so core area. So essentially core area is the SoC area, the XY, your keep out, your decaps, your power delivery, your memory. So if you compare, Lakefield is obviously on the right-hand side, and I have the Gen-1 and the current generation Y TDP boards. So as you can see from the picture itself, the board area of Lakefield is less than half of other boards that we have done. Primarily because of the SoC area, right? So the SoC is 12 by 12. Now you compare with other SoCs that we have done in previous generation, you're looking at 20 cross 16 or 26 cross 18. So that itself is the majority of the reason why you have a core area which is much smaller than other boards. In addition to that, the memory is POP, like I said earlier. So you save compared to other designs at BGA, right? So you save on the memory space as well. And in the power delivery, what we did is we took a different approach. Instead of going with discrete VRs or going with fiber, we actually took a PMIC approach. So we have two PMICs in Lakefield. One Grow and Castor Grow. So one PMIC for the compute die and one PMIC for the base die. So if you look at all the combination of all this optimization that we did, so our core area compared to the previous generation is less than 40%. So it's like a fundamental change in terms of how board designs have been done now with Lakefield, primarily because of the silicon design. Okay, now let's look inside what is Lakefield, right? So as I said, Lakefield is basically two dies. Your compute die in 10 nanometer. So all the compute IPs that your core, your graphics, your media, your display, your imaging, all the IPs that are compute-centric are in the 10 nanometer die, right? All these IPs, like you see in Lakefield, These IPs are very similar to what we have in Ice Lake, which was recently announced, right? So with some optimization for the segment that Lakefield was targeting, right? So for example, display, we had to enable full concurrent displays because the converged mobility segment, we believe that you need more concurrent displays. So as a result of that, so we made modifications on display. So similar for camera as well. So we are supporting like 6 concurrent camera. That was again because of the requirements coming from the form factor. And then imaging core, I already talked about DDR, because the factor is POP, you're able to get much higher frequency. So all these IPs are there in the Ice Lake, but with some modifications, like I said, and one major difference being hybrid architecture. So instead of the regular, all the cores combined together, whether it is small cores, or rather Atom cores, or bigger cores, in Lakefield, we've taken a hybrid architecture. I'm going to talk a little later on the slide. But essentially, that's what you have in the compute. All compute-centric things are sitting in a compute die. And then below, what we call the base die or the bottom die. So all the IPs that are not compute-centric, your IOs, your peripherals, like USB, your PCIe, your audio, everything that is not compute-centric, that doesn't need to scale to the 10 nanometer, all those IPs are sitting in the base die. And those dies are stacked together with the technology we call Foveros, okay? So on this slide, the essence of this slide is to say that, so basically you have like, a tremendous amount of variance in the kind of transistors that you need to build different computes these days, right? On one end, you have desktop CPU, right? So you need higher performance, but you can afford to burn more power. On the other side, you have iGPUs or you have mobile CPUs where performance is key, but power needs to be much lesser. You have to operate at a much lower TDP. So that's the challenge you have. Like I think other like Lisa also mentioned, others also talked about this, where that's the challenge in industries. Like how do you build with this? How do you build a transistor which is optimized across different design points? The answer is you cannot do it, right? So you have to come up with a different mechanism to optimize. So that's exactly what we did in Lakefield. So if you look at Lakefield, right? So like I said, we took all the compute IPs and build them in 1274, which is our latest generation 10 nanometer process. And everything else, whatever is not compute-centric, we build them in a P1222 process. That's a process which is most ideal from a leakage perspective for all the IO processing, for any processing which does not need to go in a high compute space like graphics or CPU. So as a result of the fact that the dies are stacked together, instead of putting them in a configuration like an MCP or an EMIB where you have your disadvantages in terms of X and Y dimensions, or you have disadvantages because of the fact that power is not going to be that efficient. So you take all things out by stacking the two dies together. So it kind of behaves like a monolithic die, right? So you have the flexibility of designing IPs separately in different process technology, but you put them together. So as a result, it looks and feels like a monolithic die, like I showed you, right? So that's the biggest advantage of Foveros technology that we have brought in with Lakefield, right? So one of the main advantages looking forward as well is that you can actually build real IPs based on the process technology that is optimized for that particular IP. You can build CPUs in the process technology that is ideal for that CPU, whether it's a desktop CPU or a lower grade CPU. And then you can do the same thing for graphics or IOs for that matter, right? And then combine them together in a technology that gives you the best performance, at the same time it gives the best power. And what other thing that this slide tries to capture is that this is not one-off. I mean, we have a plan to keep building SoCs like this in future as well. So we plan to go forward with 7 nanometer. We're going to migrate our compute die to 7 nanometer. And the base die is going to migrate from P1222 to 10 nanometer and forward 5 nanometer and 7 nanometer respectively, right? So the main thing is that this is not one-off. We're going to keep building SoCs like this in future as well. All right, so I'm going to just walk through how Lakefield Foveros is put together. Like I said, you have a mobile form factor 12x12 package, and then you build a base die. essentially think of this as all the IOs or SRAMs or low memory logic, everything that does not need to be in compute die, we build that in a base die. And then you have a high bandwidth, ultra low power die-to-die interconnectivity with the scalable TSV to deliver power. And a thermal solution to take care of any thermal dissipation because of the fact that you're stacking multiple dies together. And then on top of that is a compute die, a 10 nanometer compute die, which sits on top of the base die via the die-to-die connectivity. And last not the least is your in-package DRAM. Like I said, this is a POP memory configuration where you have memory in the package itself. We have two configurations that we support in Lakefield. We have a 4 gigabyte memory, or you can also do a 8 GB LPDDR4 4X. So with that, I'm going to transition into hybrid. I'm sure you guys know about heterogeneous compute, right? I mean, it has been there in the industry, especially in the mobiles for a while. So you typically have a small core and a big core, you combine them together, right? So whatever is not heavy on CPU, you run that in a small core, and then everything else, what is CPU-centric, you run it in a bigger core. So in Lakefield, we did what we call hybrid compute, right? So we kind of combined big and bigger cores together. It's not small and big, it's big and bigger. So big in this case is your Atom Tremont cores, the latest generation Atom CPU. We have 4 of them in Lakefield, and then you combine with Sunnyco, which is the latest generation CPU, same as an Ice Lake. So we combine them together in a construct called hybrid. So anything which is heavy on compute, you run that on Sunnyco. Anything which is heavy, which needs fast response time, bursty workload, you run that on Sunnyco. And anything which is light compute, which does not need like Sunnyco like out of processing, you can offload that onto Tremont. It's very simple. So you sort of get the best of the two worlds. You get the best compute, and at the same time, you can save on battery life or hobble because of the fact that you have an availability of Tremont cores in the system. Okay, so these are power versus performance charts. So blue represents Tremont and yellow represents Sunnyco. So as you can see, right, so the fact that we have hybrid, if we had not, just think of this as if we had not done hybrid, where you had combined a big core along with Tremonts, on the left-hand side is your ST single-threaded performance. So our performance would have been limited, right? So this is exactly the reason why we went with hybrid. Right, so as you can see, certain things come sort of obvious from the chart is that the fact that we have both the cores, the entire range is extended. So you can go from tens of or hundreds of milliwatts all the way to multiple watts of power. So if you're not done hybrid, you would have been, you would be either in blue or in the orange curve, so to speak. So as a result of this, the performance advantage in single-threaded cases is up to 50 to 60% gain compared to if we had not put in a hybrid Sunnyco along with Tremont cores. So that's on the higher side of the TDP. Similarly, on the lower side of the TDP, as you can see, the fact that we have Tremont, you can actually run power-efficient workloads which don't need Sunnyco. We can run them on Tremont. So as a result, you can get a much, much wider range of performance because of the fact that you can run on both Tremont and transition and run the threads on to Sunnyco. So the performance gains, like I said, is about 50 to 60% on the higher side of TDP just because you have Sunnyco along with Tremont. The right-hand side chart, they show the same blue represents Tremont. The fact that we're able to put in 4 TNT cores instead of putting another Sunnyco, you can see the advantage in multi-threaded performance gains, right? We have a similar gain, about 50 to 60% improvement compared to if you had not gone with a four-core configuration, so stick with a single bigger core, right? So you take the advantage of multi-threaded performance gains. At the same time, you can take workloads, real workloads, and run them on TNT, which is much more power efficient. And as a result, you can extend the battery life, which was one of the intents for the segment that Lakefield was designed for. So all right, so talking more about the hybrid architecture, right? So basically what we have a dynamic feedback mechanism from the hardware going into the OS, going into the software, where we give indications that where a particular thread or where a particular application can be run, right? So anything which is performance-centric or needs quicker response time, low latency, you give an indication to run those threads onto Sunico. And similarly, anything which is background threads or doesn't need the same kind of horsepower that is in Sunico, you can offload or you can give an indication to run that on a tray mount. So on the chart, as you can see, the blue or purple, that is an indication of Sunico kicking in. And yellow or orange is an indication of tree mount. So as you can see, when you start, let's say you open a browser, you click on a browser, you're getting the data, you're rendering the content, right? So at that time, not everything you have, your Sunico takes a dominant factor in running. So you do a lot of processing on the Sunico. And then once the rendering is done, once the user is just looking at the data or scrolling down, you can actually go and run the processing on the tree mount. So you take the advantage of power efficiency by running those threads on tree mount. And then let's say you go and click on the next browser, you press refresh, again, Sunico kicks in, gives you performance advantages, and then goes in the background. On the extreme right side, you can see it's all tree mount, right? Everything that is background, whether it's your wireless scan or your inactive tabs or your email client, which is refreshing data, all that stuff can be run on tree mount and get the advantages of better battery life. So now I'm going to talk about standby. Like I said at the beginning of the presentation, is that one of the pillars of Lakefield was to get the standby power much, much lesser, similar to what you typically see in a smartphone, right? So we've done gen-over-gen standby improvements within Intel, but in Lakefield, the requirement was to bring it down substantially. So if you compare Lakefield on the right-hand side, it is 1/10 of standby compared to the previous generation. Primarily because of the 3D stacking that we've done, how the IP partitioning is separated out between compute and the base die. And then we've done other things like VNN removal, we've done USB DDR5 improvements, low leakage transistors. All those things contributed to an extremely low standby power compared to the previous generation. Okay, the graphics performance, right? I mean, it'll be incomplete to not show any performance advantages, right? So graphics, both Manhattan as well as, this is real silicon data. So Manhattan as well as 3D Mark 11, we have at least 50% gain compared to previous generation. That was one of the things that we really wanted to achieve, is improve the graphics performance compared to previous generation that we had. All right, so this is my last slide. So a lot of first things in Lakefield. Lakefield introduced the first in the industry, a real product with 3D stacking and AI hybrid compute. It's the first complete compute SoC in 12x12x1 with a standby power in the order of 2 milliwatts, in between 2 and 3 milliwatts. Lakefield is designed for low power to enable new, thin, lightweight, always on, always connected devices. And Lakefield architecture has significant improvements over previous gen-over-gen. Like I said, 0.1/10 of S0IX. It has PCB core area less than 50% of previous generation. The graphics performance is more than 50%. And the product is real. As I showed you the silicon. It's in the final phases of getting ready for production. And we're targeting end of Q4 for production samples. That's it. I can have Wilfred join me for any Q&A.
Nantech. Throughout your talk, you've said 10 nanometer, 10 nanometer, 10 nanometer, but then you said it's the latest generation 10 nanometer, which is 10 plus, which is what Ice Lake is based on. Can you confirm whether it's 10, which was using Cannon Lake, or 10 plus as in Ice Lake?
It's 10 plus, same as Ice Lake. So I mean,
Okay.
I generally classify them as 10 nanometer. It's the same process as Ice Lake.
Okay, thank you.
Hi, Javi Delacruz with Xperi. You mentioned the interconnect between the die being low power and high bandwidth. Could you describe, what it is? Like, what is the bandwidth, and what is that interconnect?
It's our, if you think about our classical PC implementation, we have a 2-die MCP. It's the same link which we have converted into a 3D link. It's a 4-rows die interconnect. It's definitely because of the higher bandwidth. It's much more parallel. It's roughly, the way we have done it is we have cut all the serialization between the CPU and the PCH to implement this die-to-die link.
Hi, Jeff Smith, Citadel. A couple of questions, maybe backing up a step to make sure I understand what the technology is, just at the packaging level a bit. So this is face-to-face bonding of two dies, correct?
That's correct.
That's correct.
So could you guys talk at all about the delivery of I/O and power, from the outside system through the bottom or the sides? Does this look like a wire bond thing, or is it vias to the bottom layer?
In this particular product, we have a combination of everything. So let me explain what's happening. So you have I/O on the base die that goes out through TSVs to the package, and it goes out to the external board. You have I/O, which is high-speed I/O like DDR, which is on the compute die, which goes through the die-to-die, face-to-face connections, back into the base die, and through the through-mold vias and into the POP package. And inside the POP package, you have wire bond pads into the DRAM die. So those are the level of different interconnect in this product.
Okay, thank you.
Don Draper. So what is the pitch and height of the die-to-die interconnect?
So Lakefield is our first product where, and a lot of different considerations were taken into account to make this really high-yielding, low power, being able to test it. So we chose a 50-micron pitch for this connections. They're roughly about 20 microns in height, 50 microns pitch.
They're micro bumps?
Yeah, there's a micro bumps, yes. Mm-hmm. And these are solder-based micro bumps.
Yeah. And the top die, the compute die, and the base die, the I/O die, can they function independently, or can they only function together?
The way you should think about our PC architecture is like the PCH is a PCI device, so it can just work as a separate device. It can be tested independently. The compute die can function independently, tested independently. So you can have these devices tested at least totally independently. But the overall functionality of the PC has to only come together when you put it together. But to your question, this from a known good die, they can all function and be tested separately.
Yeah, we actually tested it separately. Right? I mean, the TPT is a little different, so you get the base die sort of sometimes earlier. You actually test it separately, so you have the capability.
Okay, thank you.
So one more question, if I may. So if there is a substantial amount of vias going through the base die, what sort of overhead do you guys pay for just the keep out zones around those vias?
So so if you think about it, this is on P1222. P1222 is a 14 nanometer technology with 22 nanometer looser rules. So a lot of issues on TSVs are due to stress and strain or the warpage of the base die silicon. So there are some keep out zones to just make design friendly. The rules are actually very forgiving. They're what we call radial rules. There are many different classes of circuits which can be placed next to the TSVs to make the area tags. So you wouldn't want to put your highest speed SerDes next to it, but other things like decaps, power gates, maybe even SRAMs, you can have them abutting next to the TSVs. There are other issues from manufacturing, hermeticity, other things which come in, which are first order. But at least on this product, the rules are very easy to deal with. On the overhead, different design styles actually have different classes of overheads. What we found is from a synthesis, that's from a place and route. The way we constructed this TSVs, they're a TSV via middle process. They're very friendly for place and route. In fact, one of the feedbacks that we've gotten was to make this design very friendly with internal and external CAD tools. So the TSVs are very friendly for synthesis. The issues are mostly with analog design and SRAM design. They have other things from analog, like noise, inductance, and other things that are not just TSV rules that you have to take into account to make this work.
And if you guys want to scale, this technology to, higher power segments,
yes,
and you have, substantial amount of power, maybe going to a GPU on top.
yes.
How does that affect the design rules as far as, pumping a lot of amps straight through the base die up to the top and, having strain affecting?
So We don't see big limits. In fact, the way we designed Foveros is we think it'll span the entire range of the computing spectrum from the lowest end devices to the highest end devices. We also see no limits to the die-to-die scaling. It's just a question of when the technologies are ready, can be ramped up to high volume, high yield. We have implemented different means of power delivery. So it all just comes down to working out the losses that are appropriate for your segment. But fundamentally, I don't think we see there's a big limit from adopting 3D stacking to many interesting products across a wide range.
Thank you guys very much for your great talk and your great answers.
Thank you.
Thanks.
Leader Duan from Alibaba Damo Academy. Can you please comment on the possibility of stacking even more dies into this architecture and also the thermal ease of this architecture?
Yes. So Foveros is it's a chip-on-wafer process, and because of the close match of CT between silicon and silicon, again, like as I said, there should be really no limit to the power limit. We see that the yield of attaching many chiplets on silicon should be very high. So there are other limits, practical limits in terms of architectural partitioning, but from process, assembly, and yield, our goal is to drive it to many chiplets.
Okay, all right, thank you.
Thanks.
Let's thank our speakers, Sanjeev and Wilfred.
Thank you.
Our second talk for this session is on Jintide, which is a hardware security enhanced server CPU. And it'll be presented by Al Lo, who is a research scientist at the Institute of Microelectronics at Tsinghua University, Beijing. Al has also received both his master's and bachelor's and master's degrees at the same university. And he's also a co-founder and CEO of Cataphract with Microelectronics, which specializes in security chips and hardware security solutions.
You don't have it? Oh, here. This one? Okay, thank you, John. Okay, good afternoon, ladies and gentlemen. Today, I would like to share some of our thinkings on hardware security and present our work, Jintide, a hardware security enhanced server CPU. Hey. Oh. I'm sorry. Hey, it's not working? It's not working here.
Sorry.
Oh.
We have a little.
Okay, can you? Maybe. Okay. Okay, first, let's take a quick overview of the platform we designed. So on the right, basically it's a x86 server. And in this server, we changed two things. One is DDR4 DIMM. We replaced the register clock driver and the data buffer with our design. So we call that chip a memory tracing chip, or MTR for short. And another thing we changed is we integrated two extra dies into the CPU package. One is called the ITR IO tracing chip. The other one is RCP, Reconfigurable Computing Processor. So later we explain what they are used to. So this is the outline for my presentation. And we'll go through the motivation, the platform architecture, chip design, and finally the conclusion. Oh, thank you. Okay, first is the motivation. So I think after Spectre and Meltdown, we do not need to talk about the importance of hardware security. But today, I would like to see it from the customer or the end user's point of view. If I spend a few cents to buy a chip like this, 7400, I may get a spec like this, and the function is quite easy, so that I can easily prove these two are equivalent. But today, if I spend hundreds of dollars to buy a very complex chip, for example, a CPU, and what I get is some spec which has some block diagram and some software that can run on it. So the problem here is we do not know what's inside this complex chip. Especially, we do not know is there any function that the user does not want. So why this problem is so important today? There are two reasons. First, today the IC industry is so complex that IC design and manufacturing may go through different flows, and these flows may be controlled by different companies in different countries all over the world. So the flow is becoming uncontrollable. Second, today, a complex chip, for example, CPU may contain billions of transistors, where inside these transistors, we know that we can add a few gates to generate a Trojan, and there are also papers talking about we can insert some malicious function by parasitic capacitor or even by doping. Not to mention that there are all kinds of vulnerabilities we cannot avoid. So think about this problem a few years ago. We believe that it's almost impossible to prove if a chip is 100% secure. But how do we gain customers' trust? One way we think about it is we can do runtime surveillance, which means even the chip has some problem, we don't care. And what we want to make sure is at runtime, this kind of malicious behavior does not get triggered. So that's our idea. 3 years ago, we decided to start a project to design a CPU chip that supports users to verify the behavior so that they have confidence in this chip. So the idea is quite simple. First, we trace the CPU and the system behaviors, and then we check if the behavior matches the expectation. Trace and check must be done in runtime, and we call this method the dynamic security check. Users' security expectation may include, first, does the chip work as the user manual or datasheet indicated? Second, is there any unrevealed subsystem that get activated? Third, we do not want any vulnerability or debug feature get abused. So next, we introduced Jintide platform. So we selected the server, x86 server, as the start point as our design. Okay, this is a very common x86 server you can buy from the market. We decided to add a few tracing circuit and checking circuit into this platform so that we can trace the physical signal of the CPU. So we know that the CPU may have some tracing features, and we can also use software to trace this kind of information. But we believe that only by tracing at a physical level, only by tracing the signal at the CPU port, we can get the real system behaviors. So there are a few questions we need to answer before we move on to the implementation. First one, how do we perform the check? How do we perform the security check? And our answer to that question is we can identify those legal behaviors. For example, we can use a Gomes model to generate the expected behavior, and we think these behaviors are on the whitelist. Second, we can ignore those non-harmful behaviors. And we need to report those behaviors that is suspicious. So to support this kind of check, what do we need to trace? So we decided to split the CPU's execution into small intervals. For each interval, we can record the architecture state, the register at the beginning of the interval. We record everything happened during the interval, and we record the system architecture and all the registers again at the end of the interval. And the nice thing is we do want this system to still be useful. So we do not want to have too much performance penalty due to this kind of trace and check. So we need to use sample approach. So this is the architecture we designed for the Jintide platform. So on the left, as you can see, we have 3 chips. One is called the MTR memory tracing chip to record everything between the processor and the DIMM. And we have ITR to trace everything between CPU and all the peripheral, including the I/O hub. And we have a chip called RCP to read all this trace data and check if the CPU's behavior is as expected. We also have a layer called DSC firmware. DSC means Dynamic Security Check. This firmware layer will be an assistant for us to do all kinds of checking and tracing. So on the right is a figure to show the check flow. As you can see, the check flow is quite similar to IC verification. We have behavior model-based and we have assertion-based, which means we can check some of the security attributes during runtime. And next, we want to talk about the sample approach. So we know that the checking the CPU's execution is much more complex than execution itself. So we can only choose a few of the intervals to be checked. So first one we need to determine is the sample window length. So we decided to set the sample window length to 100 microseconds. It's a small window, but even so, we need a trace buffer size up to 2.56 megabytes per DIMM. And we need 100 kilobytes for each LAN of the PCI link. So totally, for Skylake we used in this case, we have 52 LANs, including upstream and downstream, and we need a total buffer of 10.4 megabytes. This is a huge memory on chip. And for sample frequency, if you need to check the behaviors, and we need to actually replace the CPU's behavior according to some golden reference, for example, the instruction set architecture. And so because we want to replay at ISA level, we need to eliminate the impact from microarchitecture such as cache. So to make sure all the transactions are shown in the memory tracing buffer, so we need to flush the cache for every time we check the CPU. So this is on the right is the diagram for the tracing and checking sequence. So you may say that this will reduce the security we gained with this approach. But the problem is we believe that the hardware security issues is very difficult to be triggered. For example, in the case of Spectra, you need to use the vulnerability again and again to get the leaked data. So if the same malicious behavior gets triggered multiple times, or multiple machines may have the same malicious behavior, we can detect them. So that's the idea of the sample approach. And then we'll take a look at the chip we designed. So this is a Jintide chip, and one of them is the I/O tracing chip. It's a big chip. It is about 300 square millimeters and running at 500 megahertz. At a huge TDP, because it has so many SerDes, it has about 136 PCIe LANs, Gen 3 PCIe LANs. And for most of the LANs, the chip acts like a switch. So the PCIe TLP goes through the downstream port to the upstream port and sent to CPU. At the same time, the TLPs get recorded. So this is the second chip we designed. It's called the Reconfigurable Computing Processor. Inside this chip, we have 3 microprocessors running at 1 gigahertz. And we also added some encryption and decryption features to this chip, including PAF, OTP, and TRNG. We have 2 reconfigurable logic array here in this chip. So these two reconfigurable logic array are just arrays of PEs. We use this circuit to accelerate the instruction emulation. So this is the multi-chip package we designed. This one is called the Jintide CPU. It contains 3 dies. So the pinout is almost the same as normal Skylake, except that it have higher power, it have higher TDP due to we added 2 separate dies in this CPU. Other features of this chip include we can also provide secure boot feature to the platform, and this feature is provided within the CPU package. For example, here RCP can work like as the root of trust in the MCP package, and we can get the BIOS through ITR and the PCH, as if the RCP chip is the central processor here. And we can also verify or identify all the device which is connected to this platform. Second thing we can do is we developed a few APIs so that user can use all these kind of API to do the tracing and the memory. The idea behind the Jintide project is that we hope that users are able to trace the system behavior. User can use their own algorithm, use their own judgment to check if the system is hardware secure. So this is, as a summary, the Jintide platform and Jintide chips. So we designed the x86 processor with dynamic security check. And we can run a system check at 1 Hertz. And the measured performance loss on average is less than 10%. And we have, for each check interval, we have 100 microsecond check interval. And we are tracing everything at physical layer, which means that's the real behavior. We're not relying on any software or CPU provided features. And we provide the algorithm to replay everything we traced and check if there are any unexpected behavior. Other values of this platform include secure boot and encryption offloading. So this is our performance loss versus the detection probability. So in this platform, if we sample too frequently, the system will be impacted and the performance will be lower. So the green dots are all the measured results. On the left, if we sample every 10 seconds, and the performance loss is very little, and it's only less than 1%. But if we sample 10 times a second, and we have a performance loss of 22%. All the performance data are measured by SPEC CPU 2017. And so we just discussed the sample approach. Our idea is that if you have multiple machines and maybe the bad behavior is triggered multiple times, and maybe on different machines, M stands for different times and plus different machines. And even with very low detection frequency, sample frequency, we still can get a very high detection probability. It's on the left corner, on the right, on the top. So let me explain a little bit how this kind of structure can detect a Trojan. So we use this as an example. It doesn't mean this kind of attack can perform on current platform. But this is a kind of a microcode attack on a commercial CPU. If the microcode is attacked, so in one victim process, the program is using some AES instruction to encrypt the data, and the key is provided to CPU, and the microcode, the malicious microcode will store the key to some internal register which is not visible on ISA. And another process can easily use another key to trigger the malicious behavior and to load that key previously stored and use that key to decrypt any data that is previously encrypted. So with Jintide platform, as we mentioned, we replay whatever the CPU did. So if the malicious behavior gets sampled, and our play is done according to a golden reference model, the instruction set architecture, so the malicious behavior will not get replayed, and eventually we'll find some mismatch, either output or memory state mismatch, and we'll report this kind of behavior so that this malicious behavior gets detected. The second thing we would like to discuss is, can we use this platform to detect the vulnerabilities, the CPU vulnerabilities? So here we take the Spectre V1 as an example. Actually, if we only use ISA, means the instruction set, the architecture set, and the instruction set architecture to replace the CPU behavior, we cannot detect any malicious behavior that is caused by the microarchitecture vulnerability. So we need to extend our replay to microarchitecture level to add some microarchitecture element here. Here we use two things. First, we use a virtual cache in our replay. So with this virtual cache, we can also record the status of the system cache. Sorry. So for this cache, it does not need to be 100% match the actual hardware cache. And we can also do speculative replay for each branch that could cause to speculative execution. And we record all the address that is accessed in one speculative branch. We call that SAL, speculative address list. So the target to detect Spectre V1, we need this criteria. All the probe target is loaded by the prediction branch. So, we mean the probe target, for example, in this case, which is the array 2, it's in SAL, but it's never in the vcache. So following this, to check this with this criteria, we can detect this kind of side channel attack, and we can determine this is kind of Spectre V1. And following the SAL, we can also restore, we can also go back to the secret that is leaked. So the next question is, can we use this platform to detect all kinds of microarchitecture vulnerabilities? And we do believe that by extending the behavior checking model and move to the microarchitecture model will help detect such vulnerabilities. And there are also a lot of vulnerabilities, and our observation is that we cannot use one general rule to detect all the attacks, and not all the attacks can be detected by rules. So finally, the conclusion. So we designed a platform, we designed a CPU called Jintide. It's hardware security enhanced. And our idea to increase the hardware security, to increase the hardware trust is by tracing all the physical behavior of the CPU and use the ISA model to check if the behavior matches the golden model. So we designed the chips, and we also did some experiment on the performance versus the detection ratio, and we expanded how to detect Trojan and the spectra with this platform. Finally, I would like to take this opportunity to express our thanks to Intel's expert on this for their great help on this project. I think that's all I have. Thank you. Okay, I will invite my colleague, Dr. Zhang, to join me to answer questions. Thank you.
Hi, Ian Cutler, Symantec. Great talk, guys. Always nice to see a Xeon used in a different way. You've got a hypervisor which the OS is loaded through a hypervisor, and you control everything through that. But how are the chips actually, how are your custom Jintide chips actually connected to the CPU? Is it through the on-package PCIe lanes?
Yes.
Okay, thank you.
Shai Gilon from Ravel. How would somebody verify that your chip doesn't have vulnerabilities and does not introduce new attacks?
Yeah, thank you. That's a very good question. So, our chip used very open architecture. So all the reconfigurable computing processor inside that processor, we use a reconfigurable computing array. It's just an array of PE. For this architecture, we can easily avoid a higher hardware security level because you have redundancy. You can program the architecture at runtime. You can change everything. That's one thing. And the other thing is that we do not need to prove our system is 100% secure. We trace everything. We provide the data to the user so that they can check if this is reasonable.
But that can still introduce an attack by your chip on the server being tested, right?
So I'm sorry?
So you're intercepting all memory and all I/O transactions. That means that your chip can actually create attacks on the server being monitored.
Right. So, okay, that's why we need a lot of encryption features inside this chip. For all the data we stored, for all the data we collected, we store them with encryption, and nobody can read them out.
Okay, thank you.
Thank you.
Hi, I have a question about the golden reference model you mentioned for checking. Did you build that yourself, or could you elaborate on what was used?
I'm sorry, what's your question?
The golden reference model for checking, did you build that yourself, or did you get it from somewhere?
So actually, at the beginning of this security check, we developed the POC from open source project Box, and later we almost rewrite all the code so that most of the code are developed by ourselves according to SDM, Software Development Manual.
Okay, thank you.
Thank you.
In fact, we also have some modified parts of the box to let it be suitable to the Xeon processor we traced. So yeah, we do lots of work to modify the open source code.
Hi, sorry, me again. Can you apply this technique to anything apart from a Xeon? Can you use the same chips to say on an AMD x86 CPU or a Power 9 or an ARM CPU?
I think this technology, this idea is universal, which means you can apply to different architectures.
Sure, the idea is, but are your chips locked to the Skylake design?
I think the I/O chips here we designed is for the Xeon Skylake.
Okay, thank you.
Thank you. Okay. 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 Thank you.
Thank you.
Thank you. Thank